Hello, everybody, and welcome to another wonderful day of physical chemistry. So far this semester, we've built up a set of equations for possible wave functions to describe the behavior of quantum mechanical systems. And we've shown how they fit into a set of operator equations from which you can actually get useful information out of those wave functions we've already constructed. Now, that leaves us with one real big question. What are going to be the form of our operators? So it turns out in quantum mechanics, almost all of our operators can be built up from two common operators, so two common equational forms, position and momentum. So let's start with the seemingly easier operator, the position operator. So this is defined as x hat, and its equational form is x. You're literally multiplying your wave function by the position of the system. So if you want to try and determine the position of a wave function, what you're going to need to do is apply your your position operator to your wave function, which means you're going to need to multiply your wave function by x. So for example, this turns the wave function cosine kx into x cosine kx. So this seems fairly straightforward, except for we won't run into one immediately very pesky problem. Is this going to generate any set of eigenvalues? And here's where we run into the issue. In order for it to be an eigenvalue, when I multiply my wave function by my operator, I should get my wave function back and a value. Instead, I have a variable. This means, in general, the position operator doesn't actually end up producing any eigenvalues. So a lot of our useful eigenfunction eigenvalues break down for the position operator. And as such, we're going to be ignoring this one for now. It's very important to know it exists, and we'll learn some good tricks with dealing with it later. But it turns out while the equational form looks straightforward, its application is actually quite difficult. So let's go on to the other operator. This one looks like it's going to be trickier, and that's the momentum operator. So in order to determine the momentum of a system, you can apply our nice momentum operator, which is given as h bar over I times the derivative of our function with respect to position. So this one looks like it's going to be trickier, especially what with having an imaginary number in an operator. This looks terrible. But in actual application, it's actually not too bad. So I should be able to determine the momentum of my system by applying my momentum operator and getting back a momentum eigenvalue, with again leaving my wave function unharmed. And we can also give this in Dirac notation as applying the operator, get the eigenvalue, leave our wave function or ket unharmed. So we can actually apply this to some simple wave functions we've generated so far, like e to the ikx. So let's figure out what's going to be the momentum of e to the ikx. So for that, I need to apply my first derivative with respect to position. So when I do this, what I get back is h bar over I, because this stays unaffected. And now I get ik from the first derivative, and then I get back e to the ikx. So ik e to the ikx. And here we are luck into this wonderful scenario where we have I over I, which is just 1. So we're left with h bar times k e to the ikx. And this is actually quite nice, because the whole idea is that my eigenvalue should just be my wave function times a numerical value. Here my numerical value is h bar k, which means the momentum of the system is h bar k. This means I've got a forward momentum based on our Planck's constant and that k value, which, as you may remember, gives us a lot of information about the wavelength of the system. So if I know the wavelength of the system, I should be able to back out the momentum of the system. And again, with a forward momentum. However, we're left with an interesting question. I can also have e to the negative ikx. Now, what's going to be the momentum eigenvalue for e to the negative ikx? Now, this one we can actually do almost by inspection because I generate a negative value here, which when I take the first derivative comes out front. So I'd end up with negative h bar k. So if I have a positive e to the ikx, this means I've got forward momentum. But if I have a negative e, if I have e to the negative ikx, this gives me a negative momentum. So forward movement, backwards movement. So that's going to be the big distinction in between these two wave functions. And again, this is some very cool information we can get just by applying our momentum operator. Now, with these two operators, momentum and position, we can pretty much construct almost any other operator we'd ever want. But the one we're usually most commonly after is going to be the Hamiltonian, which again, constructed by position and momentum operators. So an easy place to start with is kinetic energy. So we're going to ignore any potential energy and just focus on our kinetic energy term. Well, we can get kinetic energy classically by taking the square of the momentum over twice the mass. Well, 2m is just the value, so it's not going to be an operator at all. It's just going to be a constant out front. And squared momentum, I can get that by applying the momentum operator twice, one after another. That's going to be the same as the momentum squared, which means I can get the kinetic energy by doing 1 over twice the mass, applying the momentum operator twice, which in classical form is going to give us a second derivative. This h bar I, both the h bar i's can come out front, which gives me h bar squared over 2m over I squared. But I squared is just -1. So that negative comes out front. And this leaves us with an operator that you're going to have to become very familiar with. This is our kinetic energy operator. If you want to know the kinetic energy of any system that at least is one-dimensional, we can go ahead and use this operator. In order to get multidimensional kinetic energy, it gets a little bit more complicated, but we'll get to that later. However, turns out kinetic energy isn't everything. So we can combine our kinetic energy operator with a potential energy operator to get an overall one-dimensional Hamiltonian. Now, this gives us the question of how are we going to construct our potential energy operator? Well, this is usually going to be done using the position operator, because by its very nature, the position of a particle is going to dictate how favorable it is to be in one location versus another. Now, since some of the most dominant forces for the potential energy of an electron is Coulombic potentials, let's go ahead and see what this looks like. So classically, we describe the potential energy due to Coulombic interactions based on 1 over 4 pi times the charge of each of our particles. So particle 1 with particle 2, and then the distance between them. Well, congratulations, you can do this same process in operator notation. And this means that 1 over 4 pi, well, that's a constant. The charges are just going to be a constant depending on the system. This means that my only variable is, oh, it looks like the position operator. So in this case, we can express our potential energy with 1 over the position operator. And then we can go ahead and combine this with our kinetic energy to give us a generalized form. Now, I want to use this as an opportunity to summarize some cool features of our new Hamiltonian structure. So first of all, one of the things that's worth noting is if I have a wave function with a low curvature, so this is something that's widely spread out, not located too much in any given location. Well, what is this going to mean for the second derivative? Well, this is generally going to give me a fairly small second derivative as the slope isn't actually changing that much at any given point. And since this second derivative is fairly low, this also means that my kinetic energy is fairly low. There's not a lot going on there. Now, something very interesting happens if I have a highly curved wave function. So if I have a highly curved wave function, what this means is that since my slope is rapidly changing, it quickly goes from a slope of near zero to a slope that's very positive to zero to very negative. Now, this very quick change is going to give me a fairly large kinetic energy. So again, low curvature, low kinetic energy, high curvature, high kinetic energy. Now, the question is why? Now, one good way to think about it is if I'm very delocalized in position, it means that essentially my system is moving back and forth fairly slowly and it's keeping me all in one place. However, in order to keep me in one place with a higher kinetic energy, this means I have to be moving fairly quickly back and forth. And if I'm moving quickly, this means I have a high velocity and thus a high momentum and thus a high kinetic energy. And that's really what we're seeing with this curvature. Now, one of the things that's really important when trying to apply this is seeing what happens when I apply a potential energy term. So let's go ahead and do a classic potential where we have kind of an inverse relationship with x. X increases, potential decreases. Now, one of the important things is that our total energy for a particle should stay constant, which means as position changes, what we're really doing is changing the ratio of kinetic energy to potential energy. So here, when I'm mostly potential energy, this means I'm going to have a fairly low kinetic energy, which means I have a fairly low curvature. I'm moving fairly slowly. Whereas when I get way out here into the deep end, very little potential energy, most of that energy is caught up in movement, which means I'm going to have a fairly rapid change in my curvature as I have a higher kinetic energy. Now, this actually has some really cool implications as far as position, because you'll notice that we have a lot more probability out here. So I'm much more likely to be found in the shallow end than in the deep end. I move quickly through the deep end of low potential space, and I tend to get caught up and slow down in these shallows. And this is a very cool feature of our Hamiltonian. And so again, focusing in on our kinetic energy, we're generally seeing that most of our wave functions have, if they have great curvature, great kinetic energy, low curvature, low kinetic energy. And this will be fairly useful as we go forward. However, next time, we're going to be diving into some more technical features of our operators, which will make them more useful as we go forward. So next time, more properties of quantum operators. Until then, take care.